All right. So that is my solid that I had uh just as far as we got when we opened this up on Thursday. But I did peruse through the supply documentation. So I found out, where my housing sheet was that I'm referencing here, that I've got my solid made. Just one simple sketch and extrusion is all I've done so far. What I was saying is that I did post my if I go to my courses here real quick, enter. So just in our courses under our screw conveyor, I did for the screw conveyor solid assignment, which is what we're still working on. I'm trying to get it done by the end of the week is what I'm trying to do. I do have an image of how mine ended up, and I did upload that particular part and how I made it. So if you prefer to just kind of like dig through how I did it and continue, we can. There's a few corrections I'm going to make because I've determined some bearings that we'll use, and so the hole patterning could be a little bit different. I think the hole patterning I've put in mine for a lot of the holes that are in it are just from the SEMA standard, and then those have to maybe get modified once I actually have a part that I'm looking to match up. And so I think the bearing hole mounts changed a little bit from what the SEMA standard would be, but that's just to fit the bearing. So that's not like a disqualifiable change. It's just that I've got to make a change to fit the bearings that I'm going to use. So that might be the only change that you might see me do here, but from this original solid that I posted. But you can see how I think I've even, painstakingly maybe even named my extrusions, kind of went through and renamed kind of my order of operations when I built it. Kind of trying to be pretty thorough. And I would be on a normal solid, I'd probably be pretty thorough. I might build it without naming everything as I build, and then I might go through as one of my steps before I would like throw this into a library and maybe help somebody out that's going to work from this solid in the future, name some of the stuff. There's a lot of drafters and designers that don't do that, and they just leave it with just extrusion one, two, three, hole, and that's fine too. You can peruse through it pretty quick to highlight the things that those are driving, but maybe good designer practice would be to, uh, especially on like base component type modeling, to name it, be a little more thorough maybe. So I'm going to go back and start doing this. All I've got is the main housing. I got it like 8 foot long, and it's got the correct dimensions to kind of resemble the volume of what's inside the conveyor is kind of how I designed that. So essentially this solid is made to kind of fit inside how I'm going to build it. Um, and so what I'm going to do is just kind of look at the discharge and the inlet and kind of look at some of the data for that. So I'm going to go over my over to my solid that I have and do some more solid creation on here. So this is my front view here. To me, this is going to be maybe my discharge end. This is going to be my inlet end over here on the back side. So to me, front view is going to be, and that wouldn't matter so much if I decide to do this the other way and have my inlets or discharge on one way. I just need to I'm thinking about it as what I'm doing. It's just thinking of which way this is going to be. And it wouldn't matter necessarily, but so just for me, I think I'll put discharge on the kind of the front end side here. If I pull up my standard real quick, this was all I was going to do for the housing. I only really did just the U-shaped part that fits inside here, and I didn't do anything going on here because I'm going to put that into the sheet metal part that I'm going to make from this housing. So at this point, I'm kind of done with this particular sheet in my SEMA manual, and now I'm going to go and look for the discharge sheet stuff. So if I just scroll through here, I can't remember. They're kind of in close proximity to each other. And the more you scroll through this thing, the more you'll get used to it. So here are some end plates. These are trough ends. And I'm not quite ready for an end plate yet because I'm just ready kind of for the discharge. There's some bearings. And then I get into shafts and flights. So I can't remember where. I think maybe they're down below the housing stuff is where the discharge and inlet data is. So let me scroll down past our housing print, which the housing wasn't until quite late it was like page 33 in my document. Then we got covers. We've got supports and footings here. I need yeah, so we'll see. Okay, so here we're getting into feed and discharge spouts. Okay, great. So let's see if they give me some variables and some dimensions here to work with. So I'm kind of doing a on the way my conveyor is going to be designed is it's just going to drop into a squared around and then be ready to fall into a pump tank. So, I mean, in some ways you could say, well, why don't I just do just a rectangle discharge and dump it in? And I'm like, yeah, it's pretty common on discharges like this that I might funnel almost like into a funnel is kind of how my squared around ends up being at the end of mine. So I end up do wanting kind of a flanged fitting to bolt like a funnel on the end or a squared around transition. And so I think so this is my flush edge, yeah, flush end discharge. I think this is, so between this sheet and maybe this sheet, I got to bounce around them a little bit. So beyond that, it's hardware. So I think I'm just going to stay on these two sheets. Looks like I have some stuff highlighted. Here's the diameter of my conveyor. So if I'm building this thing, it looks to me like it discharges this A dimension, which is 7 7/8 from center of my auger down the end of kind of this bolt-on flange where my squared around is going to bolt up to is only going to be 7 7/8 long. And then what is dimension B? Oh, just how long it is this way is 11 inches. And it's kind of hard to see this. I can zoom in a little bit easier. But this B is what I would call as kind of an ID dimension. So you're seeing a profile of a conveyor here. It's showing kind of metal thickness here, of like what this is built out of. And ours is going to be 12 gauge. We determine that on the housing sheet. So this is kind of like a 12 gauge thickness, and it looks like B to me is kind of like ID to kind of the end of my trough here. And then I would have this like end plate on. And the reason why we have like these bolt-onable end plates is so you can pull the auger out if you ever have to. And so ours is going to be designed to where it's kind of like this, essentially, really like very similar to this is what I'm aiming for right here. And it's just able to be unbolted on this end and the other end. Some conveyors, screw conveyors, they may only bolt on one end, and then the auger would maybe have to be pulled out through there. And some unplate end plates are modified different so that they don't aren't completely disassemblable, but that you could disassemble them enough to pull the auger out. But eventually, you got to think of maintenance, is why we think of when things go together, we also think of having to get them apart to do maintenance on them. Augers wear out over time for sure. They get worn in. If an auger rubs on its housing, if the bearings fail on it and it sits there and the auger rubs on the housing, eventually the housing wears through. So really, I mean, like the SEMA standard manual is to make things so that they're replaceable parts on these. You could buy a whole new housing if you still had a good auger. You could buy a new auger if it was ruined and the housing was still good. So you can kind of like buy the parts you need to keep the maintenance up on them. And that's smart design process too. It's smart design process because you make money when you sell the thing, you make money when you sell parts for the thing. And so if you make things that are kind of like serviceable and parts replaceable, yeah, kind of, that's money in your pocket. Except for they'll probably outsource that work to someone else and or they'll do it in-house themselves. There was a lot of augers we built that we were just copying somebody else's design and rebuilding it from scratch, but with an old one as an example. So anyway, so I just want to pay attention to these dimensions. This is A is overall two to kind of when I put my flange on mine. So I'm going to think of these dimensions and go in here and add some extrusions to my housing. 7 7/8 and 11. And so if I go into my and I might not I haven't like sat there and studied my old part. I mean, I built that last year. I haven't gone in and actually I'm not trying to build it. I mean, I'm not trying to build it different, I should say, but I probably am doing it in a little bit different order than I did that on the original one. For whatever reason, I looked at this and thought, oh, I'll start with the discharge end. And okay, so what I need to do is have this thing from the center of this go down that 7 7/8 and kind of be like 11 inches wide from here. And so all I really need to do is start an extrusion that is kind of that rectangular shape. So I would do that off of probably a plane so I've already, I've strategically put this up. So here's center plane on my housing solid. There is center of where so where this plane and this plane meet are going to be the center of my auger, right? Just by the way I've built this This particular plane is on center of my pipe, my center pipe of my auger going through here. So that's kind of the cross section of where my center pipe's gonna be. So I really feel like I can use this plane to work from and develop an extrusion from here down. Because what I'm gonna have is I'm just gonna join this as one solid. And so I'm not making individual parts here yet. And so however I choose to extrude this, it's just going to be kind of joined into this solid that I have. So I don't have to worry about it like, building off from this curvature down. I can just build it through this and make it be part of it. So I say I'm gonna start a sketch here on this plane. So I'm gonna start a new sketch here. I'm gonna kind of flip it around so that I'm looking at it. And I could turn on this plane, but this is I'll turn it on really quick. This is the plane I'm using to draw with. And I'm really gonna draw like right here. So I might even do like my F7 slice graphics. So this just cuts whatever my solid is to where my plane is that I'm drawing. So I use F7 a lot to slice to this. And all I want to do is build that little rectangular box that I'm going to extrude 7 7/8 kind of towards me in this view here. So I'm going to pick this one. I'm going to project some geometry for this just to lock it into. Like maybe I only really need this edge here or even this end surface. To me, I'm projecting that. It kind of has my width already involved right there and the end of my conveyor. So to me, this is good projection geometry, which I just need is construction. And then I'm going to build just a rectangle. I'm going to lock it into that endpoint that I just projected and pull it across here. And maybe I'm going to pull it long like this. Sometimes when I want it to be bound to this point here, but I don't have that geometry out here where I'm drawing. So I'm just going to draw it like big like this and leave it for a minute. And then I'm going to constrain it back to the end of that projected line that I have like this. And that's really what is constraining the width of that now to match the width of my solid, which is 11 inches. That's the ID of that conveyor. And then I just needed to know the dimension from this here. So what I've done is I'm just kind of drawing this shape and I'm going to extrude it down from there. So what I need to know is this B dimension, 11 inches is how wide they're saying kind of the ID of this discharge will be 11 inches by the width of which they show here in this like B is 11 by 11. And that makes sense. My housing width is 11. So it ends up being kind of a square on the end here to drop product out and down and away. So so I'm going to just add that dimension here to this. I think with one dimension, this will be constrained 11 inches. That matches my SEMA standard, pretty simple sketch. And I'm going to just finish that. And then I'm just going to extrude that shape. I just need to know how long. And SEMA tells me, oh, well, from center of auger down to where you would bolt anything onto it. It doesn't mean that's the end of the discharge. It just means, hey, this is a good place to terminate at least the housing discharge. And then you can build a flange and bolt up to whatever you want to go to there. If you're going to drop into a piping system, if you're going to drop into, whatever kind of equipment, you might need to put a chute on here to direct it into some other equipment. So they just, by putting a flange on a discharge at this is just kind of preparing it to be like however you want to take the discharge from here, have at it. All we're telling you is maybe pull it down 7 7/8 away and put a flange on it there, and then you know build it however you want to after that. So I just need it to be 7 7/8. So I'm just going to use that exact dimension here and know that that is kind of like from center to the pretty much where I'd bolt anything else onto it. So that's kind of an OD dimension there. I mean, these are ID dimensions in some ways. And this is kind of what I would consider, which you would think ID is diameter. Don't forget that for your test. It's just that I use it interchangeably as kind of an ID dimension, inside dimension, and an outside dimension. I use that terminology the same as I would for ID, OD, diameters. But so don't let me totally confuse you. It's just in my terminology, the way I talk. But yes, and it matters when I'm working with sheet metal, whether it's ID or OD. So I am paying attention to the thickness of what my parts are going to be, which we haven't even explored yet. I'm just building the inside solid. So I'm going to say extrude this thing though, my particular little profile, which is already selected, and it's 7 7/8, 7.875 is 7/8, 7.875. That's going the wrong way, so I'm just going to extrude that the other way. And that's all I need it to be. I'm going to have it joined to that solid. That's what I mean. Like here, I'm not making a new solid. This is just joined, and then I just say, okay. So kind of looks like that now. And I can stay with this for a minute. So now what I have to visualize, if I want to build more on this, and you can tell from the assignment that I posted here, I've built more on the solid than that. Here's that what we just put on, but I've also built on the flange that's going to go on there, and even some of the end plate here. So I can spend a little time just doing these now before I ever go to the inlet end. And sometimes I think systematically like that, like I'll just kind of work on this end. But what I'm going to do is I have to envision that this fits inside my part. And so when we get to where we're actually going to make a part from this, we're going to be able to like use these faces and just like thicken them in a sheet metal. There's a thicken command in sheet metal, and right here I actually have it right here. Thicken and offset is a modify command. So if I'm in a sheet metal, I'm actually in just a standard part. I'm not in a sheet metal part because this is a base solid. When I go to bring this in and derive it in to make some sheet metal parts from it, I'll just use this thicken command, but I will have already programmed like it's the thickness of the sheet metal that I want to build this out of, which is 12 gauge. So what's going to happen is I'm going to bring this in and start like thickening it and using this solid to just thicken from it and make my parts that match this contour. And then I can make them into flat pattern parts because of the sheet metal functionality. And so, and laser cut parts after that. And so what's going to happen is this thing is going to be what I call is going to be skinned in sheet metal. And so when I'm going to build other parts from that, I kind of have to always I have to think of that. I have to think that this is gonna get bigger as I put sheet metal on it. And so anything that I'm going to build from here too, I need to account for that. And this can get a little confusing, but bear with me, especially once we start building parts, it'll make sense a little bit. So it'll be maybe a little bit abstract here what I'm doing, but once we start making sheet metal parts from this, it'll be a little more obvious. So what I want to do is build the flange. So in my SEMA manual, it just shows that there's a flange that's going to be here. And I'm going to kind of do it like they show it here. I'm going to incorporate some of this flange into the end plate. Like they've bent like this plate top and bottom to kind of make an end plate to bolt on to the end of this conveyor. And then they've finished off, like they don't have any holes in this flange here, but I'm like mine, I think I put some holes in this side here so that the holes that are here. So I make kind of a rectangular shaped flange is what we'd call that. It's just going to be a square rectangular flange, but it's going to be a mixture of parts. And and how I would attach that to the sheet metal is I'd actually weld this together. So this particular sheet metal part is going to become welded, or this plate part with holes in it for a flange is going to become welded to the sheet metal of the housing. These are going to be welded joints. And some of them are going to be bent joints though. So it's going to be kind of a mixture of parts going on here, which I don't think maybe they give you some. This is mostly the flange hole patterning that we're looking at for feed and discharge spouts. I'm going to have to know this eventually, but maybe not until I get my flange built. So let's build my flange here. This doesn't really show it as like three-sided, or it kind of makes it look like it doesn't go that direction. In mine, I'm just kind of planning on it being like four, like it kind of shows right here upside down. Like if this is my discharge, the only difference is I've shoved my discharge clear to the end plate. So I'm incorporating the end plate in with the discharge, and it's just I could make one like this, I guess, and pull my discharge back and leave a little bit of room in the end of my auger here. And there's reasons, I think there's design standards why I might do one way or the other. Um, some ways, in a lot of places, they'll avoid this just because it sometimes I have to put some backwards flights on my thing to like make sure that anything that does pile up in the end there also gets augered back into the spout. If I put my discharge spout like somewhere in the housing in the middle, you sometimes have to have backwards flights to push stuff from either end into it. And so I'm going to avoid that complication by pushing my discharge clear to the end plate, which means my flights on my auger will just push everything to where they start falling off the end. And generally, I think the good rule of thumb is we can check SEMA standard on this when we get to the auger, but generally, whenever you're designing an auger and into a discharge, I think the rule of thumb might be to make sure you put enough flights on your auger to go about halfway into your discharge. Like, don't just let them come up to the discharge and end the flights on the screw. Like, let them kind of carry about halfway across that discharge. And then as it'll continue to convey stuff as it starts to fall off. Plus, if it kind of packs in towards the end, it'll let it keep carrying it to where it can kind of drop it into the whole discharge chute that's available. So there's definitely some strategy involved in, how far the screw goes into the discharge area. I think a good rule of thumb is about halfway and or maybe one pitch or something, but there's definitely a good rule of thumb. Don't just go up to it. And anyway, so I'm going to avoid this. Other than I want to build like a a square flange on the end of mine, incorporating my end plate into it though. So how that's going to look to me is I'm going to jump over here. I'm going to get an idea of what they have on these like flange dimensions. Maybe they put some on and maybe they don't. Like I think right here, this G dimension, this H dimension might be kind of handy to me. So I'm going to come up here and see what I highlighted here for my 10-inch conveyor screw. Um, they're saying this is 14 or 10 gauge. I think they give me a range here. I think is that the flange? It's a little bit confusing on whether that's like the parts of the sheet metal for the discharge or if that is the flange itself. I view this as more of the sheet metal for the metal coming down, and I'm going to make it match the housing, which is 12 gauge, which we haven't done anything with yet. But then what is it going to tell me over here? Aaron, let's see here. That's the ID of this, the ID of my discharge is 11. That's kind of what I've designed mine at. It's 11 by 11 little square that I just extruded. What is B? B is the minimum dimension from end plate over is going to be 9 inches, I guess. I might be breaking that rule a little bit. I guess we'll see what I am. Is that to center line over? I'm 11. Hmm. Yeah, I'm bringing mine to the end, regardless of what they say. What's C here? I'm just kind of getting a feel for what these variables are. C is probably that 7 and 7/8 that I've already drawn on there, so it's kind of redundant again. G and H, that's kind of maybe what I'm looking for is what are these outside diameters of the outside distances of these flanges. So I have G and H being 14 and a quarter, what they're telling me here. Overall flange size, 14 and a quarter. J must not apply to me, but I don't know where J is here. Where's J? Okay, so yeah, a little bit different measurement here. I didn't highlight it. And then K, what is K? Maybe it's kind of coming in off the flange. Now we're starting to talk about the whole pattern sequence here. They tell me I'm coming in 5/8, and then L is 4, and then we have M, which I don't have, and then I have N, and then P. What is P? The size of bolts. They want me to use 3/8 bolts. And R is what? Oh, this would be, yeah, I guess if I had, mm, I'm thinking of why I would have kind of this little over a discharge. It's kind of interesting. I don't have that kind of a fit up on mine. I'm trying to think of, it's interesting. It almost feels like more of like an inlet end. And is this inlet and discharge? Feed and discharge. Yeah, I guess so. We're talking more of an inlet end over here. So it's going to help me on my other end. Okay, that makes sense. I was thinking they were all just discharge shots, but they've kind of incorporated discharge and feed into the same kind of drawings and chart here. But I've got to kind of remember these dimensions. I think the one I'm going to go out start with is this 14 and a quarter here, because that's kind of how big my square is, G and H. And so what this looks like to build kind of the flange for this, I can just do a sketch on this face. That's a good place for it. This is the end of my solid here. So I think I'll use this face as my sketch plane. So I can just select it, right? Do a right click, do a new sketch or a new sketch and pick that face right there. This is where I'm going to build the flange for this. So I'm going to project that geometry. So I'll pick this whole face and project it onto my, because I'm going to reference this whole square in order to base this solid off of. So what I have to remember is this is a solid that fits inside, and then it's going to get skinned essentially with 12 gauge kind of all the way around. especially around the three sides. Like this side won't have, this side will kind of be open here, and I'll have a bolt-on end plate. This end, this side of this surface will be skinned in 12 gauge, and this side will have a 12 gauge skin on it, and so will this side. So around three sides, it'll kind of be 12 gauge around this. And then I'll have a big end plate that bolts on. So it's kind of a weird thing here, but what I want to do is offset this thing, the thickness of my skin. So I might just pick like this is going to be a reference, essentially a reference. I'll change it to construction material, but I'm going to offset it now. That whole square. I'm looking to offset it the skin thickness. Well, we don't know what that is, right? Where you're like, well, what is 12 gauge thickness? Well, eventually you start memorizing these, but I did do, if you work in the sheet metal industry, that is. If you don't, it takes a longer time to memorize some of this stuff. But I have in our modules here for the screw conveyor resources should be our sheet metal gauge chart here. So screw conveyor resources. I'm just going to pull up this sheet metal gauge chart right here. So if I open this one up, it's one that I think we've used before, and so I think we used it in last class a little bit. Our housing needs to be 12 gauge, so 12. These are the gauges. Number 12 gauge shows me how fractional thickness that would be, 7/64ths. Or right here, and oh, by the way, ours is stainless steel. It's a food product based screw conveyor. So our thickness of our 12 gauge in for stainless steel is 0.1094 is how thick that is. And so I'm going to initially offset my square that much. Of course, if I was working with galvanized or steel or aluminum, I would have slightly different decimal equivalents of that thickness. I feel like a lot of people forget that. I mean, I do remember that I like this chart too because I had the millimeters in parentheses there. So, but, and you'll find that if you do work in the sheet metal industry, you'll probably print a copy of this and have it pretty readily available while you're designing stuff, or at least have a digital copy that you pull up while you're working on stuff. But so I'm going to offset at 0.1094 initially, 1094. So I'm going to do that offset again and put in that number. 0.10, oh, sorry, it's point, yeah, 0.1094. I think that looks correct. So that's kind of what like that'll be the space that my skin takes up around there. Um, yeah, it's point one. It's actually 0.1094. Yeah. 0.1094. That's 12 gauge. The funny thing is this is going to be a welded joint. So this falls into if I only offset it this far and then I skin this solid with 12 gauge, then if I go to slip over this flange, I will be doing what's called like a size on size. So I will have like made my flange ID to match exactly what in a perfect world, in a theoretically perfect design, how tight, the skin would fit. And we have to this is something that um, definitely takes some experience, but we definitely need a little tolerance here. And so we want this to be a little bit more than the skin. Uh, Otherwise, I won't be able to slide that flange on in the event that it just doesn't totally theoretically exactly match and it grows a little bit like materials tend to kind of do. I would end up liking to have a little bit extra gap so that this can slip on and then be welded onto the skin. So I need to go back into like a standard sheet and set what I need is like a standard tolerance for welded joints. And so I'm gonna make one up here on you right now. I'm gonna say that a real nice standard tolerance for welded joints might be, and I'm just gonna try to I could do a 16th. That's a pretty big tolerance. That would be like a 32nd all the way around. If I make this particular offset 1/16th bigger than I really need, then when I went to slip it over, I would kind of have like what is like a 32nd all the way around it of tolerance, like a 0.03. That'd be like 30 thousandths all the way around. That's pretty decent for a welder and a welded type fitting. Um, I wouldn't probably go much more than that. So I think what I want is about a 30 thousandths clearance all the way around this. And so I think I can just go in here and add 30 thousandths to this. I just want to think of a nice, easy number. So here's what it would be if it was theoretically exact and perfect, and I left just enough room for just the skin that I'm going to put on it. But in reality, I need a little more room than that, so I don't have to force somebody to grind to fit this on. And my parts, when they're laser cut, maybe has a better chance of just slipping on to fit. And so I'm going to add, I'm just going to say that's my sheet metal dimension. I'm going to say plus 0.03. That's 30 thousandths. Kind of looks like that if I put it in. And I'm going to hit enter. I added 0.030 to it, 30 thousandths. That's big for a machinist. Like 30 thousandths, you're talking, that was a big jump to a machinist. For a welder, for general fabrication, or for, and I think of a welder kind of working in a little bit working in like finished carpentry, kind of, maybe even finished carpentry being a little even to a higher standard than even some welding fits. But, if you're looking at finished carpentry, maybe 30 thousandths is still a pretty sloppy fit for finished carpentry. But for welding, it'll work good. 16th, yeah. Finished carpenters probably work in 30 seconds of an inch pretty easy. Maybe even 64ths. So framers on your house, this is going to be way too tight of a tolerance. They're going to be working in eighths. Eighths are going to be really tight tolerance for a framer, maybe quarters. Yeah, realistically. So they work in a, yeah, it just depends on your trade and what the tolerance might be that's common. And so then this ends up being, so if I offset that, I should end up with being 30 thousandths all the way around bigger, right? Or do I need to go bigger than that? Oh, sorry, don't delete that. That would make sense, right? So my ID of my flange ends up being right here, 11.27, um, which I think would be correct. Yeah, yeah. Let me just do a little, yeah. 2788 is what that ends up being ID. I'm going to lose once I what I did by just adding that 1/32 or the 30 thousandths to one side is I've got 30 thousandths this side, I've got 30 thousandths the other. So really I'm like kind of 60 thousandths overall width bigger by just adding that, if that makes sense to you. That's kind of what I'm showing here is that I'm at 60 thousandths larger, which is close to a 16th of an inch in kind of tolerance on this welded joint. If that looks a little foreign to you right now, that's fine. Like we're going to do quite a bit of this kind of calculations as we build out the parts here. And we'll find that sometimes we miscalculate when I'm building my solid, and all I have to do is go in and I don't find out until I'm starting to skin it and I start to see like interferences with my parts. And then I'm like, oh, I got to go back to that solid and make some small adjustments to how things are fitting. And so I can come back to this base component to make some of those adjustments. So I don't have to get them right, right? I'm trying to take my best guess to get them right. But it's not the end of the world because I can just come into a few of my sketches and change like, oh, that's where I miss. I see interference now the parts are fitting together. That's a pretty common design process that you kind of guess wrong sometimes. But this is kind of the border of where my flange might start once I have skin on this. And so now I'm going to actually do the dimensions that are on that sheet for kind of how that flange would look. And I think I'll build it out as a full square, but I know that I only need three sides of it because I'm gonna bend the other side into the end plate, which is a removable end plate, so I can remove my screw. So what I'm gonna do is I'm gonna build this out kind of like this, essentially what they have going on here. I've already kind of done the G and H dimensions. That's what I've just put on. Well, I haven't done that yet. I've kind of done the inside, the A dimensions, but I've done my A dimensions so that it'll slip over, is kind of how I've done mine. Because my A dimension is just 11 inches. It's the ID of it. I'm thinking of my flange and thinking, oh, it's going to be slipping over some material. So my A dimension ended up being, plus 60 thousandths from A, 11. Yeah, that makes sense. Okay, but what I want to do is, so I kind of might need to remember that when I reference this, or I can just go to this size. Yeah, let's just go with the chart size of G and H. So G and H, that's at 14 and a quarter. So I need a square that sits over my square that's 14 1/4 square. So if I go back here, I'm going to say I'm going to build another square, or I could offset that, but I think I'm just going to build another square, oh, out here somewhere, and then I'll constrain it where I want it. Um, and it's going to be 14 1/4. So I'm just building this out here in no man's land. I'm going to move it over to where I want it. 14 1/4 by the same, 14 1/4. And rather than use two different mentions for that, I'm just going to select this other one and say that it's going to be a square. So I'm going to use that as my dimension. So it's 14 1/4 by 14 1/4. Then I just want to constrain that right over the top of my other square. So I can just sometimes when I do this kind of stuff, I might draw like some construction material across here. Like I have a construction square that's projected, so I'm just going to draw in a line corner to corner on this. Because there's no, I wish, I kind of wish there was like a geometric center like CAD has. Sometimes I have to build my own geometric center sketch work a little bit. So I'm just drawing a cross line on this particular projections. I'm constraining it to those projections so that if those projections change, this will also go with it maybe. If I don't get that, if I don't there, I didn't get the constraint right. So I just need to make sure I do a coincident constraint to that little corner there. There we go. Now, if the projected geometry changes, this is going to switch for me. It makes an intersection point where I should be able to like move this over there, although I might have to draw some construction material on this as well. So, but not necessarily. I can use geometric constraints, I think, here too. Like I can say, oh, horizontally or vertically in this case, constrain the center of this to this center point here. That's one constraint. Then I'm going to go the other direction and say, and you see me do this a lot with geometry, like constrain from midpoints to some geometry that's a midpoint like that. So with that's only a single dimension input on the flange, and then it's just geometrically constrained with the projected geometry. So if that projected geometry ever changes, I should hope that this stuff at least flexes with it. That's the power of constraints, right? We're trying to make a plan for changes in the future. So that's actually what my flange would look like there. I could actually extrude this thing, the thickness that the flange should be to become a part. Only while I'm in here, I might as well just maybe put the hole pattern in this same sketch so that if I'm ever going to come in and work on this flange, here it is the over, here's the sizes of the flange plus the hole pattern. I think I'll sketch it in here, the holes. And so I don't know what this made. I don't know what this ended up making this, but it's like from here to here is 1.4856. So it probably, if I would have gone with the dimensions itself, I would have ended up with probably an 1.5 inch width flange around here. Mine's a little bit smaller because I'm kind of chopping some of that up to add tolerance to how it's going to fit. And so, which is fine as long as it's going to fit my part. And then my ODs match what SEMA tells me my ODs should be at 14 1/4. So I'm happy with this. Now I just need to lay out probably some geometry to do these hole patterns, which get kind of complicated. If you notice that from this, and if I finish this flange, we'll be doing good for one day probably. But you'll see that I'll spend more time on this on Thursday as well, and or tomorrow. Heck, I'll be spending time on this tomorrow, but not exclusively. Um, and let me um I'm just gonna stop for just a second. I'm gonna push pause because it just made me um it's funny, I got an update on my thing and now everything's just slightly different. Where's my like pause button? Pause. I'm gonna resume now. Okay, that was my tangent. So don't stress too much about that assignment. We'll do it together. And let's get back into this one. So this is, to me, I've got to really pay attention, and this is a little complicated hole pattern. I'll try to finish this before I call it a day, but if you got to take off, I'll see you tomorrow. I'll pick up where I left off first thing tomorrow. But what I'm looking for is kind of to rebuild this little hole pattern around mine. And so I've got to use these other dimensions. So really, if I'm working off the outside edge of mine, this K dimension comes in handy. And then it's kind of funny that you can see how I mean, it's a little bit confusing here, but they say it goes K to L to M to an N to an M to an N. I mean, it's like Holy cow. And I think we determined that M and N are not different in mine. So that's nice. I'm not using different dimensions for M and N. I think I'm using the N dimension for any M. I have this L dimension, which is a little bit different. And then R, which one was R again? Oh, that doesn't apply to me here. So really, I just need K, L, and M. And I've got, yeah, go ahead.
I'm pretty sure we're not gonna use M at all. We're just gonna assume, well, there's not enough room for another pole, so we're just not gonna be there at all.
For like this whole pattern does not work out. Is that what you're saying?
Well,
Or if I go K,
that won't use M at all.
okay.
Enough room for there for another.
I got you. The amount of variables they have here, I don't need this center type, which you can tell they've put that one in the center. If there was going to be some oddity or something, yeah, I got you. Okay, so let's just go across and see what that. So you're using the N, the 4 3/8. Yeah, because I'm not even given an M number on mine actually. So I'm going to assume N for M here, but I think I will use L, right? What was L? It's 4 inches. So I come in here and I say K is what, 5/8? And then I go from there, at least if I'm looking, and this is kind of interesting because you're like, well, where am I looking at here? Um, G and H, like which way is which way is the discharge like end here? And I would say they're definitely like to me, I don't know. Do I read this right? Because these are technically like three different views. I don't think I'm looking at I'm not looking at views that kind of relate to each other too much here. It's not like they're oriented correctly to each other, I don't think. Because when I look at this drawing and I see the wall thickness in dashed hidden lines here, this to me could be confusing. And maybe it doesn't, maybe I'm tripping out over stuff that doesn't really matter too much. But if I was rectangular, I might have to be a little more careful. But I'm not, I'm pretty square, so I don't think I can mess this up too hard. But you know, what makes sense to me is this could be the discharge or the very end plate end right here, where there's no where there's no kind of downspout thickness of material. If I look over here, what I mean, like, let's see on my part here, I'm viewing that this is almost oriented this way, that this is the end. And then I'm going to have like a thickness of material here and here and here around this downspout. And I'm not going to have it here because I'm going to bolt on this end plate. So the way I kind of read this, and I could be reading it wrong, but to me, this is like my end plate discharge, and this is kind of around my three sides. In any event, that's the way I kind of view this. And they didn't put a thickness across right here because it's going to be end plate thickness and not sheet metal thickness there, if that makes sense. So, okay. K, long story short, I think this is how I'm going to build mine. K is 5/8. So I'm going to maybe do some offset there. And then its L is 4 inches. 4 inches. It's just funny in this direction, it goes right to that M and N dimension here, and L in off here. Ooh, I hate this. I actually hate this flange really well, but I'm going to build it to SEMA standards, and then we can compare it to what maybe a symmetrical look would look like. So let's build it first to SEMA standards, and I'm going to pull this over on my other screen. I'm never going to be able to quite keep this in my mind without looking, at least without referencing it. So, and I can do these with, I'll probably do this just with a circle. I think I'm just going to draw in, whether you do these as points and use the whole command later, that's an optional. I think I'll just do a circle here. These are 3/8, 0.375. That's what the hole size is. I'm going to apply the same clearance standard to this hole size that I did my other. I don't know. Should I do that? There's also a clearance hole on the hole command, which is kind of handy. And in order to use the hole command, I'd probably just do the points. Instead of putting in circles, I would use points. And then I would establish those holes as a clearance hole. So that might be kind of cool because what we want is just, this is going to be a hole that fastener slips through it. So I don't want it to be size on size either. I need to make it loose on the fastener, which is a 3/8 fastener. That's the major diameter of the fastener is 0.375. So I don't want to make a hole that's 0.375 where my fastener has a slim to no chance of fitting through the hole. So it's got to be oversized a little bit. And so if I want to add my 30 thousandths all the way around, I'd be adding 60 thousandths to that. And that's so maybe that's a good. I don't know I don't know what the default clearance hole that the hole command will make. I could experiment with it. And I think that the hole command has like a loose and a normal and a tight fit clearance, which so you actually are going to have like three different options if I use the hole command. So maybe I will. I'm like talking myself in circles. This is my designer mind. I'm saying instead of that, maybe I'm going to put a point because I'm going to plan on using the hole command for my hole. So here's my point of where one hole would exist. Now I just need to dimension it to that SEMA standard, which they give me as this like K dimension in this direction. So I say dimension this from here to here is what they call K, which K is 5/8. 5/8. And remember you can type in 5/8. Remember, you can always do you could do I don't. I tend to do decimal equivalents, but it's just because I have them memorized more. 0.625 is what I'm going to enter for 5/8. That's just the location. So that one is not a tolerance dimension that I would have to be thinking about. Do I have to add or subtract tolerances? No, that's just a location dimension. 7/8 from the edge over. And then the dimension in the other way is also K. So it's K in both directions here. So from here to here is the same dimension. And so I'm going to actually enter that dimension. D10 is what mine particularly is. So there's at least the start of this complicated hole pattern. And then I can either pattern it over, I could place them and individually dimension them. I'll probably maybe pattern these over across. But it comes in over here, K to K. I could set one over there and dimension it in, or I could just like pattern these across. So maybe if I do like just a simple pattern. To me, this gets like when you're hole patterning flanges, the way that the pattern commands work sometimes aren't super helpful, other than you have to suppress some that you don't want because the rectangular pattern is going to make like rows and columns, and you can tell if you're going to pattern from here. If you'd establish your columns this way and then your rows this way, well, they're gonna be putting in patterns, parts of your pattern are going to be going across where you don't want holes. And you could do that and then suppress those over on your model browser because that's a legit thing. When you actually make a pattern, let's say you don't want to use parts of that pattern, you can just suppress them so they're not active. And that's a legit way to do it. Or you can do it. There's a bunch of different ways a person could maybe see the best way. I don't know what it is, but I could definitely pattern this as columns this way and then two rows and only do like the patterning from here to here in one pattern. And then I could come and establish a new one and go the other direction. So it's up to you in what maybe makes most sense. I don't think there's totally a good, better, best here. I think whatever you do to get these in is good. Maybe I think of the worst one to do would be to do each one individually in dimension, like with 40 different dimensions around this thing to put all these holes in. I'm definitely going to try to think of some pattern that will speed up this process a little bit. Um, and so what I mean is, I'll try to demonstrate what I'm saying here is that, okay, if I figure out what this pattern would be, if I'm going to use this rectangular pattern command and I want this point to be patterned for all my holes, I could say, okay, well, what's the direction I'm going to go? Well, one of the directions I want to go is maybe my column direction. So I'll just pick some geometry, like one of my projected lines. So I actually used one of my original projected lines. I'm going to say, I'm going to pattern it, but not that way. I want it to go this way across my flange. And what is that distance? Well, it's what they give us. It's like N distance is well, first they say L. This is additionally complicates this. So this makes even patterning this a little bit hard. I might, this is an annoying pattern. I'm going to tell you that right now. So you might see some people just try to do a symmetrical pattern around here and not exceed what SEMA standards are. Because the SEMA document that I'm following is like a standards, and I could tighten up my whole pattern if I'm gonna do something that's symmetrical all the way around this, which I think of flanges like that are the most friendly to work with. They're kind of like reversible. The pattern is symmetrical all the way around. I just would want to make sure that if I did that, if I made that design choice, that I wasn't making hole spacings further out than SEMA standard wants me to be. And so maybe I would try to do some some hole pattern in between 4 and 4 3/8 that would be symmetrical around here. I mean, that's hard to think of. You'd have to do some calculating and figure it out. If I just follow this, I feel like I can't quite go to a pattern yet because the first one they say in this direction is L, should be my next dimension. So I'm gonna do one more point on here. This would be according if I'm following my SEMA sheet, this is K dimension, this would be L over to here. I'm going to install a kind of a horizontal constraint. I want this point to always be in line with this point. So I've got that constraint now. And then it tells me that the dimension in the manual would be from here to here would be this L dimension right here, which on my sheet says it's 4. And so that's the location of second hole. Ooh, yeah, I just constrained that. Thank you. Yeah, and if you take off, just hand me your or leave your ADDA application on your table. So I'm just going to kind of keep clipping away here until I get my whole pattern built. But I'm recording this by the way. So yeah, so this I constrained mine with a horizontal constraint. Clicked there, clicked there. That'll keep those in alignment. And then I just used a dimensional constraint, and that's how it's constrained. And my thing says it should be 4. Um, it's probably likely that I actually do the other ones on this side. And I probably only need one and one, and then I don't think I need one in between, right? Like maybe that's why this works out to not needing. So what I'm saying is I could put in another point here. I mean, this is a little I'm working a little manual here, but I don't want this to be I don't want any of these projections to naturally show up. I'm just trying to place this out here in no man's land, and maybe I'll place another point. And I'm going to constrain these things using my dimensions here. This one is also a K dimension, so I can just use this. That's it. And then it was dimension from here to here. It's also K. So I'm just using K over here. And then I need that horizontal constraint. This is how I constrain those. That one to that one horizontally. That keeps those in alignment. And then I'm just going to do that dimensional constraint that my page says. My page says that should be N over here. So this is kind of weird. Ooh, I hate this whole. Sometimes I hate this stuff, but because N is 4 and 3/8. And this is what I don't love about this whole pattern is that it would tell me that if I'm just following that chart, sorry, I deleted that one, but it would tell me that from here to here should be the N dimension if you're reading it how I'm reading it. And N dimension is 4 and 3/8, 4.375. 4.375. And then it's just not constrained because I needed to do this to there. Then that should actually finish out my whole pattern across here. I'm pretty sure because this dimension is it more than 4 and 3/8 or not? Well, it's 4.65. Yeah. It's like this is an odd hole pattern to me. If I just follow the sheet, I don't love it because it's just not symmetrical for one. And I have this distance across these two holes that are that I don't love either. I mean, it's like more than 4 and 3/8. So to me, I probably end up making a modification of this to make something more symmetrical, which isn't against the rule of SEMA. It's just that and what I mean is this flange would have to go on exactly the right way, and then the thing that bolts up to it would have to be oriented the same to have the holes line up. It can be a lot harder to get that made correctly if my part is like kind of if the hole pattern is unsymmetrical in some ways. It could be installed incorrectly maybe, and then that would cause a problem. So I feel like I'm gonna pull up my other solid real quick and just see what the whole pattern is I came up with. And then the dimensions might be a little bit different. Like I said, I haven't revisited it specifically. And so I just kind of feel like if I was thinking right on my other one, I probably would have made a symmetrical hole pattern here rather than this kind of oddball. So let me just go in and just check myself here and open it up here, which is the one that I've posted in. Um, it's this conveyor solid here. It's posted up. And it looks like that's actually what I started with. I didn't know that I started the same way, but here's my discharge chute that I dropped down. I don't know if I've made the same dimensions. I would hope that I did, but and then I have the inlet chute. So it looks like I did chutes before I ever worried about flange. Here's the discharge extrusion flange. So I can kind of go into this sketch and see, oh, like what did I do here on this other solid? Yeah, it's kind of oddball. I got the 5/8 there. I'm actually at 4.33 with an oddball. It looks like I've done it as kind of a pattern. There is a pattern here. But you can, yeah, it's hard to tell. I mean, it's a little bit tricky to tell, like which pattern is which. I went like 13 in between. They don't give me that, do they? I don't think on my SEMA chart I necessarily have 13. I look like I've tried to make this kind of symmetrical. The outlier is this way. This 4.427, which is a driven dimension. It looks to me like what I did was I definitely made a symmetrical pattern here, 4.33. It's all under 4 3/8. That's a good thing that I see, except for that L dimension is kind of ignored, which is 4 inches. Um, Looks like I've made the designer choice to say, well, I'm making a symmetrical, at least as symmetrical as I can. What I'm interested is that I didn't end up with a symmetrical pattern this way. And I don't know why. 14.34, that's actually incorrect. That could be part of my problem, maybe, because that should be 14 1/4, right? I'm not sure why I ended up with 14.34. Probably because I did my tolerance and then I probably kept this at like 1.5 inches. Well, not really. I don't know what I did. It's a little bit different. I could kind of argue that this one is close but not exact. And so it's kind of an interpretation from SEMA standard to what I did. But I think I've got enough information that I know what I'm going to do on mine is I'm going to make mine symmetrical as I can. I'm going to see if I can come up with a symmetrical pattern on this on my actual saw that I'm working on. So I don't love this, but what I'm looking for is kind of wanting to put this one and this one so that they're symmetrical between from here to here, right? So I could probably figure this out. I'm going to delete this dimension or change it at least. And you've got this dimension from here. So I'm keeping this K dimension. I'm coming in 5/8. But I want to know, like I'm looking to say, what does this measure from those two that are located on the corner? Well, those two are 13 inches. Okay, that's cool. That's a nice even number too, by the way. So that's 13 inches from corner to corner. So what I have is like 1, 2, 3 spaces. So if I say this is 13 inches, 13 inches divided by 3 spaces, they should be 4.33 apart. And so I'm going to do that. I'm going to say, let's dimension these. It's kind of a not, it's kind of a repeating number, which means it's not going to narrow down to like three totally equal places because it's like a repetitive decimal number there. So I'm gonna just kind of enter it in as maybe like 4 or 5 decimal places, 4.333, sure, 4 decimal places. Maybe this will push me in accurately enough. And then I could pattern that, but since I've already got these geometry drawn, I'll just throw this in here and say I'm going to add that dimension to this one. And then I can do a quick measurement, or you can actually add this dimension. What it'll add it as is as a driven dimension, right? But it's a way to kind of track that I'll say accept that. And then I can see, oh, okay, I'm a symmetrical pattern there. I'm really driving this from just 2 dimensions, right? All of these others are just f of x. So if I would come in to modify this sketch, I would look for, oh, you know, here's one input that isn't a function. So that's one of my drivers, and here's another one that's not a function. So I don't honestly only have 2 dimensions that I'm actually using to get that pattern in there. I could copy that to the other side across the center line to get that same pattern over here or mirror it over there because that's what I want is I want that whole pattern over here and then I got to kind of worry about a couple other holes missing over here. And so maybe I'll do that. Maybe I'll say I'll just do a mirror of those. Mirror what? I'm going to mirror this and this, which are going to become holes. Mirror that and that. My mirror line is going to be some line in between here. So I think I can pick 2 points maybe, or maybe I actually need a line. I might need to draw kind of a center line here. It's a little bit annoying, I think, also to mirror, but I can't pick some geometry points here. It wants a line for sure. So I'm going to do a construction line. Oh, I'll just do it like through my whole part here. There's like a midpoint construction line that I can use that as a mirror line now. So if I'm going to mirror this geometry, I'm going to pick them here. I'm going to use this as my mirror line. I'm going to say apply, and they're showing kind of like this, this symmetrical um, constraint that's been applied to them. So those will be, that's good. And then what I've got is probably I need two more that are probably going to be this dimension here. Like this should be the same, right? I'm just going to measure this from here to here. Sorry, 13 inches. So it's really the same pattern. And so I can just say, and I might just, thinking of that, I'm probably do another mirroring thing. So I'm going to say, oh, I'm going to draw a line the other way as well, just a construction line from, wait a minute. I think I exited my, for some reason I pushed a button to exit my sketch, but I really want to put in another kind of mirror line this way. So I'm just using the midpoints of my, and I want that to be construction material. I'm just using the midpoints of my outside flange there to be good mirror lines. And then I'm going to say, okay, let's drop a couple more points here. I need one, like somewhere here. If you do project to those, they should apply that constraint, but I may have to reapply them as well. So I'm going to say I want these to appear geometrically constrained here to there, and this one here to there. That's fine. That's keeping them in alignment that way. And then dimensionally, I'm not really going to add any new dimensions. I'm going to pick this dimension that's driving them. And when you do this kind of like dimensioning where I'm selecting a dimension from a dimension, if you pick a function of one like an f of x, it's fine. It'll all just be driven by this one. So sometimes I go back to the OG one, the original. But it's not totally necessary. It's like, because on a big assembly, you might be over here picking something. And if you pick one that's being driven by, then that's fine. It'll drive it the way we'd expect it. And then this dimension here, maybe I'll dimension from here to here. Nope, I'm going to chain them together here. It'll be easier to see. And then this one I can just keep track of. Maybe I just want to see it display for me just to keep track of it, so I'll accept it. So I've got this, what I call is a better symmetrical part, and I seem to be within the range of like spacings. It's not like I'm like 5.5 inches apart, which I feel like would be potentially I'm like bolting this together too coarsely. Like at least I'm in the range of what the SEMA standard would be in that 4 3/8 to 4 range on my hole spacings. The reason is because things just won't hold together good. If you start to space these out even further, you could have some like flange deformity from bolt to bolt where it kind of harder to make a seal on it. Good, right? But then if I put them 2 inches apart, I'm using way more fasteners, and it's like way too redundant of bolting connections. But bolting connections like this are a little bit forgiving as long as I'm not like exceeding the spacing by a large amount. And some companies will have kind of maybe a standard hole pattern spacing they would be expecting. They might like this 4 inch spacing or something. But I can mirror these across. What I'm going to do? Mirror these two. It's just this piece and this one. I'm just going to mirror them across that line that I drew, which is this one. I'll just say apply, and then I'll say done. So, and the other moral of the story is like hole patterns like this are they're kind of complicated. I've drawn them out like I would almost sketch them and detail them on a drawing, actually. Like you can see that I try to keep my sketches like easily modifiable. There's only 2 dimensions in here actually, which is simple. Well, and then there's the overall flange dimension. So technically, I only have 3 dimensions. Everything else is geometrically and kind of a patterned or mirrored constraint. So this to me is more forgiving. Like when this part gets created, I can really slap it on in either direction and not have it be wrong. So it's symmetrical. And I think of that a lot in my design process is can I make this simpler or do I have to make this totally dependent on its orientation to line up. And if you do that, then it's easy for the fabricators downstream to make a mistake Not that it's your problem, because it's just if they were following their prints, they would catch that. But it gets common if things are not symmetrical. It's easy to install them incorrectly and then to weld it all the way out before you realize the part that's got to bolt onto it. I put my flange on wrong. It happens. And there's reasons for unsymmetrical stuff for sure. But in this case, I think this is the best case scenario. And so I'm going to say, I'm going to do one more thing though, and then we'll call it good for the day. All I'm going to do is I need to know that when I actually build this flange, it's not going to be in this. It's not going to be all four sides, and it's only because I'm kind of thinking of drawing. It's because I'm thinking of my my SEMA standard that I'm following over here. That I'm going to make it more like this picture right here. So I only really want a three-sided flange, and then the rest of that the part on the very discharged side, the outside of the, is going to be bent into this end plate. So I actually don't need this side of that flange. It's only going to be like a U-shaped flange is what I'm going to do here. So I'm going to come in here and make one more modification, which is going to be right here. I only want this flange from here around this U shape. And right here, this part of this is going to be bent into the other part. Is that right? Or do I need it to bolt up? No, I don't. I want this part of the flange to be in the end plate. And so I'm going to do a line, not a construction line, but I'm going to do a line while I'm in this sketch. And I'm going to say from here to here, I'm going to do a solid line that's constrained totally whichever, geometric constraint to lock that in perpendicular to right there. So there's no dimensions needed for that. I'm locking into this point to this point. It's because I'm just going to break up my geometry to only extrude the U-shaped part of this. And then I'm going to come over here and create another line from here. I might have to make it from here though, huh? Right, from here, from the very end. So I'm probably gonna change that one a little bit. I'm gonna actually draw it right here, from where the end of my solid is, and then across my flange. These are small details that you might pick the wrong spot until you go in and see how parts are fitting up. But I think if I'm anticipating correctly, this is where I want that to terminate, and then this part's going to be bent on the end plate with that whole pattern in that bend part. So this one I've got to move here. And I could delete it or I could like move it. In order to move stuff, if you want to keep and preserve your geometry, especially if you've like used that geometry for projections later, then it's really more helpful to like break the constraints and move the geometry than it is to delete and redraw. Because if you've noticed, that blows up models. It wouldn't blow me up right now because I haven't ever made anything from it. But in order to do that, you just need to delete these constraints, right? And get this like flex, keep deleting constraints on this until you can get it to break free like that. So it just took me a couple constraints to break. Now I can come back in here and coincident constraint that end to this end. So I use that technique when I know that I don't want to delete geometry that's driving something in my model downstream, and just break constraints and like move it around. Then you have less like errors show up if you've deleted geometry and it doesn't know where it was anymore. So I think this is where I want to break up that particular flange. So what this is going to look like, I'm ready to build it now. This is as far as I want to get today. Build the flange, finish this sketch, and I'm actually going to build this. I'm going to project this geometry. So or extrude it. Extrude this geometry, which is this particular shape. It should be U-shaped. Yep. I don't want it to be 7 7/8. That's what my last one was. I think these are 1/4 inch flanges, 0.25. I'm not sure if that's in the SEMA manual or not. And I'll double check that really quick. Off the top of my head, I think I'm doing a 1/4 inch flange, and it's going to be up this way too. I mean, this is critical. It's not going to go this way. I'm actually going to install this to the metal that is around this discharge end. So the part that bolts onto it will be the flange that fits right here. But this is going to be the flange. It's going to be kind of welded to my housing solid. And then I'm just going to say okay on this. I'm going to keep it as the same solid. It's like it's joined. So it's not like a new solid creating because it's just a one solid. But that's what it's going to look like. It's going to have the sheet metal that'll be in there, plus a little bit of a gap on the sheet metal. And I need that sketch to make the holes in it now. And then the fourth side is going to be picked up by the end plate bend. And so I just need to make sure I put the holes in this. So I'm going to turn back on the sketch and make it do multiple things. So I'll just turn on the visibility of it. There it is. And now I can use it to do the next part, which I only need to do the holes that are actually in that particular part. But I'll be able to use these later when I do the end plate. drawing and use those to, to cut through for a hole. So I'll make it actually the size that I want. So I'm going to use the hole command here. And then it's going to automatically maybe pick, yeah, it picks the ones that are automatically in my solid. It didn't pick those other ones, or maybe it did, and I just need to X these out and just re-pick the ones that I want for sure. That one, that one. Usually it'll be the last, whatever you use last, the default settings are what are usually showing up. So those are my 8 positions for holes. I just want them to be a clearance hole. So the hole type is a simple hole, or right here is clearance hole. So let me do a clearance hole. And then it's not countersunk, so I don't want to do any kind of special features here. So I'm going to say none, no special features, just a hole through for a bolt. And then it's just going to tell you, oh, well, what kind of bolt are you doing? Well, ours on our CMA standard says it's a 3/8 hardware. So I could say it's ANSI. Let's just keep it in ANSI. And then I just got to pick, it's just a hex head bolt. Like a regular bolt is a hex head bolt. These other ones are just a little bit different fasteners. So I'm going to say hex head bolt, and the size is going to be 3/8. So that's just telling it what hardware you're planning on bolting through it. And then this is where I was kind of planning ahead. This is kind of nice because here there's 3 different, and that was in our fasteners chapters, we talked about loose, normal, and close fitting holes. I'm just going to keep it as a normal. This is not a place for a tight tolerance necessarily. These generally are gasketed. There might be a gasket that goes in between here, or sometimes they're just silicone. Like some people, they'll just use like a caulk type silicone on metal to metal flanges sometimes, and just squirt a caulk bead of silicone and then bolt it together. And then you eliminate the need for a gasket and you eliminate like multiple surfaces. If you put a gasket in here, you have like the flange surface, the gasket surface, and the flange surface. So you create like 4 surfaces of like potential bacteria trapping with gaskets. And so some food processing places will just silicone just a tubular caulk silicone and go metal to metal and minimize how many surfaces could become contaminated. But in some situations, we do need a gasket. So this particular situation is just a run-of-the-mill basic bolt to bolt, you know, flange to flange with some silicone in it, and that's all I need to kind of to make a seal. It's really whole potatoes falling through here, so it's not like I might ooze some material, but it's not like I'm going to slip a potato out this bolted connection. So there's not a huge need for like if your product is small and fine and powder, then the gaskets probably need to be there. Otherwise, that stuff vibrates out and makes a mess if it can't stay inside. So this is it. I like this normal fit. I don't know. I guess that ends up being like 397 is just what it ends up being. I'm just going to make sure 0.375. Oh, sorry. 0.397 minus 0.375. That's the fastener that's going through there. So this is actually 22 thousandths of clearance all the way around it for a normal fit. I probably would have gone 30,000. So I would have been on the loose side of it if I would have gone like a 16th or a 32nd all the way around. So they're actually a little on a normal fit. They're a little bit tighter tolerance than 30 thousandths. 22 thousandths all the way around is what I have here. Is that right? Or not even that? Actually, I only have divide that by 2, right? I'm actually 11 thousandths all the way around of clearance. So it's a pretty tight fit, but it's not size on size, that's for sure. Plasma would be a little, yeah, a laser cut, it'll be right there. But they're still, depending how thick my flange is how accurate that gets to. The thicker the flange, the harder it is to be a straight true hole from a laser or plasma or water jet. But so I'm just gonna say okay on that. Yes, I like it. Okay. And there's my hole. And really that's ready to make that part. Like I could actually like once I go in to make that part, it's just going to be essentially recreate that solid part, and that's going to become a flange part. So that's all I needed with that sketch until I come back and need to draw the end plate, and then I'll use that sketch for the holes in the end plate. And that's probably what I'll go to next. First thing in the morning, I'll probably build the end plate that goes on here, and then I'll kind of be done with that. Oh, here's one problem I did. I just cut into my solid. I didn't pick a termination point. So I got to come in here and do a quick edit this feature. It's just that I let it go all the way through and it thinks it's through the whole solid. So in this case, I'm going to pick 2 next and pick just through these holes really only apply to this. So I picked next and I picked this face surface since I'm cutting down and through from my sketch. And now I'm not cutting into my solid unexpectedly there. So that's a better representation. So I can turn off this for a minute. And I'm going to say save on that. And we'll pick it up first thing in the morning to finish that out. And then I got to do the inlet end. Oh, yeah, that was just me. Like I came in here to the hole. It's considered the feature here. So I'm going to edit this feature. And then, a lot of times I'm using through all. It works for me in like 90% of my applications. But in this case, you can see it's going to cut where there is solid, it's going to cut through that. I don't want to do that. So I change from through all to next. But then it just needs me to select the surface that I want to cut to. And I chose here. I chose this. Sorry, I chose, yeah, here. This is as far as I want it to cut is through that surface. And then when I say okay, I stop cutting through the solid where I don't want to cut through it. And I think it's quarter inch. I don't think, yeah, that my last little bit on the top here is I don't think this specified thickness. I was going to look really quick. I'm surprised it doesn't, but it's funny of all things, it doesn't tell you. I mean, it gives you this, but I mean, I feel like this is more the sheet metal for the housing and less, and I don't think I noticed that it gave me a particular thickness, sadly. Um, Quarter inch is what I'm pretty sure. I'll pull up my other solid, but it's a really nice. It's like in the plate realm. So I mean, it's one of the heaviest sheet metals you can get. But this is my other solid that I did. And if I get out of that sketch, I bet you I did quarter inch here. I could have done 3/16. So let's see what I did. I actually did do 3/16 of an inch, but I can't remember where I got that dimension. And that might be pretty uniform on the flanges that are on the housing that they're 3/16, and then it looks like the end plates are quarter inch. Well, this is a place of like debate. Do I make them all quarter inch or do I use multiple materials? And so um, we'll keep ours quarter inch like we did today, and then we'll just talk about it in the morning when I think about it. I mean, obviously quarter inch plate is more expensive than 3/16, but I think this is where a good place to stop, and we'll pick up that conversation in the AM tomorrow. Hasta mañana, you guys.
I get to know